All right, so I'm sure you sat down, got out a blank piece of paper, and worked out some nice chair conformation drawings of cis 1,3-dimethyl cyclohexane. So let's go ahead and do that here. And this will be a confidence builder that what I draw out will be just like what you drew out. So we have two methyl groups on a cyclohexane, and although it wasn't said here, we're pretty much just going to be dealing with the chair conformations of the cis 1,3-dimethyl cyclohexane. There are plenty of other conformations that are higher in energy, but we're just going to look at the varieties of chair conformations. And if I start over here, I can pick any one of the carbons. All 6 are equivalent as carbon number 1, but I usually start over here for whatever reason. If I want the highest energy conformer, I'm going to put the substituent in axial position. So we're looking to build the highest energy conformer. So we put a substituent in the axial position. If this is carbon number 1, then we walk around the ring to carbon number 3. And here we're constrained because I might think, oh, I'm going to put the other one in an axial position as well. But whether it's cis or trans is going to dictate what position the other substituent goes in. So if this one's on top of the ring, then this being cis, the other one also has to be on top of the ring. And this is where if we're trying to get the highest energy conformer, we sort of luck out that in order for this to be cis in a 1,3 disubstitution pattern, the other substituent is also axial. So there is the high energy conformational isomer, and if you're asked to explain why, you would put both substituents are in the axial or the more crowded positions. And then if you do the conformational change to go from one conformer to the other conformer, you go chair, boat, chair, interconversion. In an introductory class, we could sort of just say magic happens, and that brings carbon number 1 down here. And the methyl group is still going to be above the plane of the ring, but now it's going to be in an equatorial position. So as you change from one conformer to the other, axial positions turn equatorial, and equatorial positions turn axial. So whereas this guy was in an axial position, now he's going to be in an equatorial position. And you can see that with both equatorial, it's still a cis geometric isomer. So take that line off so it's not mistaken for another methyl group. This guy is also a cis 1,3 dimethyl cyclohexane, but it's the low energy conformer because both substituents are in the roomier, less repulsive equatorial positions. And one thing that might sound a little bit like a trick question, but it's not really, it would just probe your understanding to deeper levels, is if instead of asking for cis 1,3, it asks for trans 1,3 dimethyl dicyclo. So many pieces to this, you really have to slow down and think to get it right. Trans 1,3 dimethyl cyclohexane instead. Now when you go ahead and try to build a high energy conformer, take the first carbon and put a methyl in the axial position. Now if you have to go trans over to the third carbon, if this is above the ring, then the other methyl has to be below the ring. So now you end up with one of each. So this is sort of a middle energy one. And if we do our magic conformational change, to give us the other conformational isomer, what it does is it turns the axial methyl group into an equatorial methyl group, and then it turns the equatorial methyl group into an axial methyl group. So there's still going to be trans. This one's below the ring, this one's above the ring, and they're going to be the same energy. They're actually going to be indistinguishable, because with one axial and one equatorial, it's the same energy as one axial and one equatorial. So if somebody asked for the highest and lowest energy conformers of this, you're going to have to tell them they're both the same energy, and you don't end up with higher or lower energy conformational isomers. They end up being the same. So interesting stuff. Different varieties of 1,3 disubstituted cyclohexanes and the various conformational isomers thereof.